Do you have a reason?
Or
True.
Do you have a reason?
Yes.
What's your reason?
Because voltage ripple, we have it when energy goes up and it goes down, and when it goes down, the energy goes down, so they're slower. So they have lower energy. And yeah.
More voltage ripple gives you more low energy electrons. Now you're thinking of that. This is something like that. And this is why more ripple produces true.
Is that how you want us to explain them?
I don't care how you explain it as long as you have a way of explaining it.
Okay, like if we put the graph or withdraw.
Look at the graphs, yeah,
Okay.
indicating the ripple. Know what the graphs mean, right? This is our kV, this is our kilovolt peak, right? kVp. And this is the lower voltage region. Which, as you notice, is not present in the something that looks like three-phase or high frequency or whatever, some other modified version which has less ripple. Yes.
so that's a true false question, and you want an explanation as well on the test, or
I would actually like an explanation. I'll probably be
Okay.
a little bit clearer on that this time. You're not going to get away with any simple true false. Yeah, but I sort of organize it in the framework of true false questions, but can you explain why it's true or why it is false?
okay.
Which I always think is a good question. How about number 2? The filament current is controlled by the tube current. Got about a third of the people responding to false.
Okay, in some places it says that the filament current is the one that controls, no, yeah,
Controls the
controls the
tube
tube current.
The
And
tube current is a result of the filament current
Yes.
and the KVP. Tube current is a result.
so it's false.
It is false. All right. So number 3, moving right along here. Before saturation is reached, KVP does not affect the tube current.
True.
False.
False, really?
They could all be wrong. You could be the lone voice in the wilderness with the right answer. Is it true? Is it false?
KVP,
Do you have any idea of what graph you have in mind?
the three current
Well, it's a question about something with saturation
that. when it
and
reaches
KVP. Which graph had saturation and KVP written on it?
Saturation is when it reaches a point where KVP doesn't affect it anymore.
Are you asking me or telling me?
I'm asking.
I want you to tell me.
From my understanding, once it reaches saturation, it doesn't affect it anymore.
Oh, wait, no, false.
It's false, it does affect it.
False.
Right? right, Rohan? Anybody agree?
I said, why don't you say
Before it reaches the saturation, the KBP does affect it. Okay.
So you're remembering a curve that looks something like this, right? Or this is some filament current.
You have it on the last page?
Probably, it might be back
It's on the
someplace.
third page, this way?
So what is the region before saturation is reached?
Space charge
Space
limited.
charge.
Before saturation, how do you identify before saturation? Pardon?
How we explain.
Before it levels out, that's all you need. So this is the region of before saturation. And according to that little sketch, does the tube current depend on the KVP? That's a big yes. So it's true. Well, this is false.
Yeah.
Before saturation, the KVP does affect the tube current. After saturation, the KVP does not affect the tube current. Easy enough. And what do you want to put down for explaining why AC voltage cannot be used to produce X-rays? Some
There'll be negative, there'll be negative electron peaks, and
negative.
electron peaks flow in one direction. If there were negative peaks, they would flow in both directions.
No, they flow in both directions. Explain. You're around it. Can we refine that just a little bit?
But you can't have negative voltage in to produce X-ray. And AC voltage will produce negative voltage peaks.
Because it will have longer exposure time?
And those negative voltage peaks, where are we putting that voltage?
The
So we
voltage
make the
will-
voltage peak, where do we put it?
The voltage peak will
Put it on the target.
On the target, yes.
Yeah.
So you want to have some kind of picture in mind. You have your cathode. You have your filament right in front of the cathode. Then you have your target, which is the anode. And basically what I'm looking for is that the anode must always be positive in order to attract the electrons. And if the anode was negative, it would repel the electrons. Who's beeping? Are you? Well, somebody's beeping. something that can be turned off?
Yes.
Please do. And of course, here's our voltage, and we're thinking, this is why this doesn't work. In those negative regions, the anode would be negative and it would repel the electrons. Since the electrons will not hit the target, if the electrons do not hit the target, you don't get X-rays. What you do is burn out the machine. All right. And the solution to this problem is
Rectification.
rectification. So we're going to take our AC voltage and turn it into a DC voltage, meaning only a positive voltage. All right. Any surprises on all of those? Take that as a note. No surprises there. We've talked about most of those things. What do we got here? Number 5. All right, here I just say discuss.
That's broad to discuss.
If the KVP is increased by 15%, then the MS will approximately double. Yeah, it's true, but discuss. Explain. Tell me what's going
On a
on.
graph, the hill of the spectrum will start moving to the right, and that will lead to the increase in average energy, max energy, and the amount of mass.
All of those things are involved, yes. So just try to have a coherent sentence or two that would be sufficient. So yes, you're right in thinking about what those two graphs are. What are the two graphs that Bouchon usually gives you for that? Gives you something that looks like that.
Because
And then what's the second one?
the area is twice,
It's got to have twice the area. Yeah. Is above it?
would that be sufficient or more?
We're increasing the KVP. How do you exemplify increasing the KVP?
We have to do the formula.
There's no formula. Just how to represent it on a graph.
Higher max energy.
Higher max energy. Because KVP is related to max energy. And we're increasing the KVP by 15%, so the maximum energy increases by 15%. But Bouchon tells us that we also get a doubling of the MAS, or doubling of the area under the curve. Approximately something like that.
So for number 5, you would want us to draw a graph, right? And
That would be a great start.
and that would be it, or we have to
No.
explain it too.
We need some words too. Definitely need a graph. Definitely need to indicate that the graph has twice the area under the curve. Yes.
The max energy is indicated by what, the little red thing?
The red tick mark I put there?
Yeah.
That would do it. Are we clear how max energy is related to KVP? They're not the same, but they're definitely related.
You want numbers in the graph?
Numbers on the graph.
Or the representation of the graph is good enough?
Not needing numbers, it's ideas more than numbers here. So, looking for some idea that would connect increasing KVP to more mass. Some other idea that would connect those things. How does increasing the energy create more photons? Yeah, how does it? There's two sort of simple ideas connected with it. One of them, the electron, projectile electron, hits the target, produces some photons. The more energy, the electron actually makes multiple interactions and can produce multiple photons. So the more energy the electron has, the more photons that could be produced just from that. Which is kind of a hard one to think about, but not terrible. What about something associated with that KVP tube current graph? Well, what's that graph? KVP tube current. You don't have it in your mind? The one that had to do with saturation?
Yeah.
Yeah, what about it?
That'd be a higher saturation.
As you increase the KVP, supposing that you're below the saturation region, what happens to your tube current?
Goes up.
The tube current goes up. More tube current means more electrons. So that's a simple way of seeing how you're increasing your electrons. So we got two things going on. One, so more tube current would equate to more MAS, more photons. And then just as a basic rule of practice, every time you draw a graph, you should indicate the average energy and the max energy. Just put it on there just to make sure, even if it's not part of the conversation. So what happens to the average energy in this case?
Increases.
Increase. Average energy here is about there, goes up from about there. And of course, the max energy increases. That's talking about those. This is talking about these two. For 60 kVp, if our kVp was set to 60, what is the maximum photon energy? And why?
Sean says it in the book.
60.
Bouchon says, what does Bouchon say?
So you just times it by E.
Multiply it by E.
Yeah.
She's not keeping it up. Write this down.
60 keV, yes. Okay, multiply it by E and drop the P. Now the Y. What is represented by the maximum photon energy? How does the maximum photon energy come about? Why does the spectrum end at the maximum photon energy?
Because it gets saturated after that?
No,
That's the peak.
it's the peak. Care to say more?
So when you have the like the peaks, like the voltage ripple.
Voltage
things,
peaks, yes.
KVP is at the top and it doesn't get any
KVP,
higher.
yes, that's what the P in KVP stands for, is the peak. So we've got our voltage at the peak. And what is that related to?
Maximum energy.
The
Of
highest
the maximum energy of what?
of the electron.
All right, the KVP is related to the maximum energy of the electron.
Oh, it equals to.
How is that?
Well, the highest electron energy are produced at the peak.
The highest electron energy is produced at the peak, right?
Was that what?
All right. Okay. And we're assuming that we have 60 kilovolt peak voltage between them at this exact point in time. So what we're thinking is we're thinking about this point on the graph here. That is the peak voltage. Yes, we have 60 kilovolts between the cathode and the anode. How much kinetic energy does the electron start with when it leaves the filament? Approximately.
The 1 point. You want the joules? That's what we did.
We're gonna not work in joules, we're gonna work in keV.
When they did.
So when the electron jumps off the filament, approximately how much kinetic energy does it have?
The same, 60 keV.
It has approximately 0.
What?
The electron starts off with approximately 0 kinetic energy.
Can you please show it on the graph how it's related and where does the zero come from?
No, I don't think I can put that one on the graph. So the anode is positive, the cathode is negative.
So when they leave the cathode to the anode, they start with 0 kinetic energy?
Right.
And here comes the
Then they
PVP.
start accelerating. It's attracted to the anode. And when the electron gets to the anode, it's got some kinetic energy. So when the electron reaches the anode, it has a kinetic energy equal to E times the potential difference. Remember, this graph is one of potential difference. This is the potential difference. All right. So just a little refresher on how electron kinetic energy is related to potential difference. And then how is photon energy related to the electron energy?
It's the same.
How is photon energy related to the electron kinetic energy?
The fraction?
Is it a fraction? That would be one way of saying it. I'm looking for something a little better than that.
It's equal to or that the photon energy is equal to or less than the kinetic energy?
Of the electron, just finish your sentence.
Oh,
And what is the big idea there?
most of it goes into the and less than 1% goes into photons, but the idea,
So the idea, why can you not have a photon with more energy than the electron? I guess that's the question I'm really trying to find out if you know the answer to.
Energy conservation.
Energy conservation. Why is it not possible to produce a photon with more energy than the electron's kinetic energy? Because of energy conservation. We can convert energy from one form to another, but we can't create energy out of nothing. Yes? Does that make some sense? Okay. For those of you who ever might take a quantum mechanics class, that last sentence is not quite true. But that gets into quantum mechanics, which is kind of fun. You can bend the rules a little bit. You have to bend them for such a short time that it can't be measured. But then you get to bend them. All right.
we're still on number 5.
Well, 5. Look, we wrote a whole page on 5. And then things related to it. I could just put that on there. There's the essay question. All right. Moving right along. Related to 5. Sort of the same game. If the KVP is increased by 15%, how would you change the MAS to keep the exposure the same? Huh? Oh, yes, Garrett.
You should reduce your MAS by half.
Reduce the MAS by half because the KVP is increased, yes. Now, would you mind telling me how you plan to reduce your MAS by half? What is MAS, in other words?
The current, reduce your current.
Milliampere times seconds.
So we're going to reduce the MAS by 1/2 since the KVP increased. And MAS is 2 current times time.
That means you would decrease your exposure time.
Or or tube current. You have your choice. You can either cut the exposure time in half. Most probable choice would be to cut the exposure time in half. But you could also cut your tube current. Decrease the filament current.
So it's either or, not both at the same time, right?
You could do both at the same time, but it wouldn't be a half, but you might do a quarter, 3/4 on each. It could get really complicated. So the answer would be to change, either reduce the tube current or the time or both. And when I say reduce the tube current, you're actually reducing the filament current. The important part is you'd have to do something here to reduce the MAS, and what are the things that you could play with? You could play with reducing the filament current or the exposure time, one or the other, or even both. That's all I was looking for there. That you recognize what MAS really refers to. Is it clear what MAS is referring to?
Yeah.
Okay, it's really tube current times time. Number of electrons on target, right? Think of it as number of electrons on target. So you're remembering that MAS is equal to a millicoulomb. And 1 electron is equal to 1.602 times 10 to the minus 19 coulombs. So when you talk about some number of coulombs, you're really talking about some number of electrons. All right, that was an easier one. Let's see what 7's gotten. Okay, yeah, here we go. 7 looks fun. So these questions are not different than you expected, right? You just hadn't thought about them in such detail?
Yeah.
Okay, the intensity is to be 15 MR at some distance. What do you expect the intensity to be at something where what changes? Step 0, identify that which changes.
Everything changes.
Everything changes in this one. So you're just making use of this nice little formula, and say that I1 is 15 MR.
What stands for lettering?
Milleranken. And we're looking for what I2 is. So we're gonna rewrite that formula for I2. Yes? Or do you wanna just do it that way and figure out I2 later? Which? Why don't we do it that way? Safer. .98, we'll call it 3. And there you go. Any surprises there? Yeah. I think that calculation you're not worried about. Here we are, back to Ripple. We did this one before. Quick and easy. There we go. Are we all clear as to whether this is true or false and how you explain it? Single phase, full wave, and half wave rectified voltages have the same ripple.
Yes.
True! How do you justify your answer? They both have 100%.
Both have 100% voltage ripple.
They both have 100% voltage ripple, exactly. And of course, you would also communicate there that you have a good understanding of what full wave and half wave rectified voltages are. Yes.
Is single phase full wave without saying rectified, is it the same? Because I mean, single phase full wave.
Oh, well, if you say full wave and half wave,
Should it say single phase full wave rectified? Or does it matter?
that wouldn't matter because it'd be pretty clear that that's what you're referring to, whether it's half wave or full wave rectified.
Okay.
But I'll try not to be misleading in any way like that. We're clear on full wave and half wave?
I'm a little bit confused, about what the ripple is the distance between the top and the bottom?
Yep.
Yes?
Yes, exactly. It's the distance measured down from the top.
Okay,
And in both of these, you're going from the peak all the way down to 0. And the one to compare it to is the three-phase full wave, where it only goes down 14% or something like that.
Portland.
Go.
So for that question, we have to draw a graph as well. We can't just explain it.
You can explain it, but graphs are worth quite a bit.
Oh, they are so mandatory. Okay.
They're not really mandatory. Some people are just more verbal, but the graphs communicate so much. If you have the right graph, don't give me the wrong graph.
Okay.
That also communicates a lot. That's not what you want to communicate. Okay. Well, what was I going for here?
Number 8 voltage ripple.
Number 9. Operating at 110 kVp. You want to keep the exposure the same, but lower the kVp to 95. Would you increase or decrease the MAS?
Increase.
Increase the MAS? So what am I, so I didn't say it and I didn't spell it out in the question. I was hoping you would recognize that, what are we talking about here?
15.
The 15% rule. It's just thinking about it kind of going backwards. You're going from 110 to 95, that's approximately a 15% decrease. So a 15% decrease in the KVP would cut your number of photons down by half.
So when you decrease KVP, you're cutting down the mass as well.
Yeah, it's just sort of another way of asking the same question. Too tricky or not? Now that you know what it is, it's not a challenge.
Hold on, I didn't finish writing what he wrote. But here's what I have right now.
Okay, how about this one? You know how to sketch these graphs? Sketch a graph of X-ray spectra that illustrate filtering and explain how filtering makes the beam more penetrating. So if that's our A curve, what's a filtered curve look like? Curve with more filtering.
The B curve will be smaller than the A curve,
Smaller in what sense smaller?
like
No.
or that the curve will be lower,
Lower,
like less mass,
less area.
less area.
Okay, I can get that. Less area.
You'll have a higher average.
Higher average, lower area, higher average.
Same,
One
Yeah.
more.
same height as the peak.
Like more to the right.
Same peak, right. They have the same max voltage. I'm just going to, do something like this.
The same target.
And the same target, yeah, let's draw in a couple of peaks for, to indicate our characteristics. Target remained the same, max energy remained the same. Average energy increased, MAS, the area under the curve decreased. Okay, so far we got we sketched the graphs. What about explaining the more penetrating part?
Cause you have more, high energy, high energy photons.
The average energy of the spectra is higher. Average energy is related to penetrating power. There's a term we have to come back to, which is part of chapter 8, which I haven't finished. We need to come back to the half value layer. I'll remind myself to do that at the end. It's all related. This is related to the half value layer. Try number 11. Okay, at one point I got creative here. Not a good idea. Okay, you have an exposure. You would like to increase the distance, and you want to keep the intensity the same. So now this has to do with those proportionality formulas. KVP, MAS, and distance. We want to keep the intensity the same though. So what is that?
That I1, I2 be like 1. What do you do,
I1,
one?
I2 is 1. Yes, thank you.
We're on
And
the
then the
page.
question is, what did I say? I said, if you change just the KVP, how would you change it? But I gave you some numbers.
So it'd
So
be
you
like
would say,
distance, distance 2 over distance 1.
so you would
squared.
say that this is VP1 squared. I didn't give you enough numbers. But she gave you some. You could do something with that, right? If I do the square root of both sides, it looks like that. What was my distance? 30 to 60? So your answer to A is that, well, KVP2 would be twice KVP1. What about for B? Now we're just changing the MAS. Yes, of course. So in order to keep the intensity the same after you doubled the distance, if you only change the MAS, you've got to multiply it by a factor of 4. And then part C, what would be the visible differences that you might see between these two situations?
When the KVP doubles, then I guess it's 4 times. I didn't explain it, I know.
That the radiograph, there'll be little difference between the radiographs because the intensity is still the same, you're just changing the.
The intensity is the same. So we have our initial situation.
The distance.
And we have two choices of how to change it. We're going to a final radiograph with twice the KVP. And your other radiograph is now 4 times the MAS. So if you had some picture here, what might you expect on the other two cases?
You'll be talking quality versus quantity. Still the same picture because.
You'd expect the same picture, huh?
Yeah, because intensity is the same.
What do X-rays do?
X-rays, they
Why are they so useful?
because they penetrate through shell tissue and some of the X-ray is absorbed, which will show up on the eye image receptor.
So in the second case, the energy of the X-rays is the same, so you would expect the same picture. Now in the first case, the top one, we have much higher energy X-rays. Higher energy, more penetrating. More penetrating means less absorbing. Less absorbing, what kind of picture does that imply?
More absorbing, so
Less absorbing,
maybe a little more faded.
a little more faded, nice way of putting it, yes. So it won't be as dark. Less contrast. Because more of the photons pass through the structure that you're trying to examine. So I'd expect in this case the contrast remains the same. All right.
Less patient dose and the higher KBP.
Less patient dose, but you're also getting less contrast out of it, so you might not be seeing what you want to see. Keep in mind that as you crank up the KVP, you're kind of wiping out your contrast. All right, move along. How are we doing? Oh, yeah, these last ones are straightforward. We've done them before.
Wait, that's changing the numbers. It's a little more tricky.
All right, so the answer to this one is 5 amp tube filament current at 40 kVp. Will space charge have any effect on the tube current? And you said
So at 40.
current,
No,
kVp,
not
40
yet.
kVp, stop here. Now we're looking for 5 amps. That's here. Will space charge have any effect on the tube current? Explain. Well, if you just went which region it's in, you could hardly go wrong, right?
I would say space charge, the space charge will not have any effect yet.
Do we agree on the point? We're right here, right? Is that in the space charge limited or
Yeah.
emission limited?
Space charge.
So space charge should probably have an
Yeah.
effect. So yes, would get you some points. Now we're down to the explain. You would like to use the word saturation in your explanation. Because saturation has not been reached, as you increase the kVp, the tube current will increase. Makes some sense, seem reasonable? Gotta move along before we run out of time here. Your other favorite picture? What's the question? What filament current will produce full wave rectified? Full wave rectified tube current of 225 milliamps at 100 kVp. So 100 kVp, you recognize that you're on this line. Next, you're looking for a full wave rectified tube current of 225 milliamps. So you're on this side. 225, you're over here. And then you read down. And you say 4.6 amps. Any surprises there? Okay. See, did I get creative on the next ones? Yeah. I gave you something really weird to look at here.
What are counts?
Number of photons. Number. Looking at the graph, determine approximately the shortest wavelength available. Zero. The shortest wavelength available.
Isn't max energy equal to the minimum wavelength?
Max energy is the minimum wavelength. Related to the minimum wavelength. So what does that look like? 60, divide that into thirds. You got about what?
75.
Yeah, somewhere, something like that.
More 75.
Let's just say 77 kVp. Let's not say kVp. Let's say 77 keV. And how do I turn that into lambda minimum? That H thing, yes. Which H thing? HC over E.
Yep.
And we'll use it in KeV. .6 times 10 to the minus 11th. And you don't want to lose points, so you're going to tell me what units those are.
I think hertz.
Nope. Nope.
Second.
It's a wavelength.
Meters.
Meters. Thank you. A wavelength is always a length in meters. All right, moving right along to the next one. Which of those three peaks has the highest average energy, and you would know how to describe it, yes?
B.
So A and, let's see, C, A and C have about the same. B is a little bit higher. The average being about there for B. All right, I want to get on to the last one. And then Wednesday, what did I say for Wednesday? Last chance for any review. We'll finish up to a few details like the half value layer, which is easy. And then we'll move on to chapter 9. What did I ask you to find here?
The filament and the filament transformer.
Yeah. So what did you highlight?
The filament would be close to where the cone is for the X-ray beam. It'll be on the left side of it.
In there.
Yes.
Okay.
And the filament transformer, I'll let someone else answer that. I don't-
Over there. There's your filament transformer. And of course, you should go through that and identify the
Can you scroll up just for a
the
second?
landmarks that we identified. Yes, scroll up to see what.
Yeah, just that. Perfect.
Got everybody there. All right.
Well, the one above, we just have to identify it.
Just identify it. But you would know how to explain what's going on. Yes, at the minimum identify it, but you should, properly studying, you know how to explain what's going on as well. You can verbalize it.
For number 16. Number
You should be able to verbalize all of this. If you can verbalize it, then you have some much better feeling for what's going on, and you can explain it to other people. It's a skill. That's why you should be discussing it to each other and challenging each other on your verbal descriptions. All right, Wednesday. And then, no, we can't move the test. Somebody asked about moving the test, but we can't move it. We're at the end of the semester, we just have to deal with it. Sorry about that.